Electrical flow is a physical system governed by strict topological rules. To control it, you must understand the geometric constraints dictating energy travel. For any entry-level electrician, that understanding begins with one specific model, the series circuit. A series circuit is defined by its physical layout. You take multiple components and connect them sequentially, one right after another in a continuous line. Because of this end-to-end connection, the charge traveling through the system has exactly one valid route to take. Unlike branching circuits where energy can split down different wires, a series layout offers no forks in the road and no alternative pathways. By restricting the wiring to a single path, you force the entire system to behave according to the strict limits of that singular geometric loop. To see those limits in action, we need to define electrical current. Current, represented by the letter I, is the precise rate at which electrical charge flows past a specific point in a circuit. That brings us to the primary axiom of series circuits. Because there is only one physical path, that rate of flow must be identical at every single point in the system. Look at the schematic. The current flowing out of the DC voltage source is exactly the same flowing through the first, second, and third component. Mathematically, we express this as total current equals the current at point 1, point 2, and point 3. The physical reality is that charge cannot magically accumulate inside a resistor, nor can it leak out of a closed loop. What goes in must come out at the exact same rate. As a technician, this means if you clamp a meter anywhere along this specific loop, you will always read the exact same amp value. This absolute uniformity of current is the starting point. Once you understand that the flow rate cannot change, you can mathematically derive exactly how resistance and voltage will behave in the entire circuit. We establish resistance, or R, as the physical opposition to the flow of current within a material. Because the current flow is uniform and has no alternate paths to take, it is forced to push through every single component in sequence. Because of this sequential forcing, the total opposition to flow in the entire system is strictly additive. The obstacles stack up. We can prove this by returning to our schematic and applying specific resistance values to R1, R2, and R3. Let's assign standard model values, 10 ohms for the first component, 20 for the second, and 30 for the third. To find the total resistance in a series layout, you simply add the individual resistance values together. 10 plus 20 plus 30 yields a final system resistance of 60 ohms. The physical meaning of this calculation is critical. The power supply does not detect three separate components. It perceives one single 60-ohm obstacle. Sequential components stack their resistances, creating a cumulative bottleneck that directly dictates the maximum uniform current allowed in the system. Now we introduce voltage, or the letter V. This is the total electromotive force supplied by the power source to push the current through that bottleneck of resistance. If the current flow is completely uniform, how is this total pushing force distributed across the different components? The supply voltage is divided across the components. Step 1. Calculate the total system resistance using the additive rule. 2 plus 4 gives us 6 ohms total. Step 2. Apply Ohm's law to find the total system current. Current equals total voltage divided by total resistance. 12 volts divided by 6 ohms yields a current of 2 amps. Apply the primary axiom that 2 amps flows uniformly through both the 2 ohm and the 4 ohm resistors. Step 3. Calculate the individual voltage drop across the first component. 2 amps of current times 2 ohms of resistance means the first component requires 4 volts of pushing force. For the second component, 2 amps times 4 ohms means it requires 8 volts. The higher the resistance, the more voltage is required to push the current through it. Step 4. Verify the math. The 4-volt drop plus the 8-volt drop perfectly equals our 12-volt supply. In a series circuit, components consume the supply voltage in strict proportion to their resistance. They have to, in order to maintain that uniform flow of current. Mathematical formulas describe ideal conditions, but real-world engineering requires accounting for physical failure. The single-path topology we defined as a strict mathematical constraint is, in practice, a severe physical vulnerability. This vulnerability is exposed by an open circuit condition, the moment a single component fails or a wire is severed. Look at our complete schematic. If a single resistor breaks, it creates a physical gap in the wiring loop. With no alternate path, the severance causes current flow to cease instantaneously. The current doesn't back up, it drops to absolute zero everywhere in the system, simultaneously. Every other component in that loop could be perfectly functional, but they are rendered entirely useless by that single point of failure. The strict interdependence of the series topology means a localized minor failure immediately triggers a total systemic collapse. This systemic vulnerability maps directly to real-world electrician standards and building codes. Household wiring demands high reliability. You need the ability to operate loads, like lights or appliances, entirely independent of one another. Therefore, this topological fragility makes series wiring strictly incompatible with standard household loads. Modern homes require an alternative structural layout known as parallel circuits, where each component operates on its own independent branch. For an entry-level electrician, the core interview takeaways for a series circuit are explicit. It dictates a single path, a completely uniform current, an additive total resistance, and proportionally divided voltage. Mastering the series circuit isn't about memorizing formulas. It is about understanding the strict physics of constrained electrical flow before you attempt to design or repair reliable real-world systems.